Hello everyone and welcome to this very interesting and amazing video. As you must be aware, we have been working with this series of videos related with electromechanical conversion systems. And one of the very important aspects when we are working with magnetic materials is the electrical power losses involved with this material. So today I am recording this video to all of you and especially for my students, and this is a very simple and very short video that it's a practical example of calculating the active power losses in magnetic materials. So without further delay, let's start this video, okay? Let me start reading this very specific statement. A test arrangement containing 1.85 kilograms of material, and this material is the material that we use for question 1, was found to have the total iron losses of Pi equal to 5 watts. And this total iron loss is obtained when the magnetic field, the magnetic density field applied to the material is 1.2 Tesla, and the frequency of the AC signal is 50 Hertz. What I am trying to tell you is that we are using 1.85 kilograms of the material that we already described in the previous video, question 1, and we know the total iron losses, 5 watts, for these operating conditions. So there are 3 very basic questions over here. The first one is to determine the specific excess loss, Px, or also known as the excess adding current loss density, and here must be the word density, and in this case watt per cubic meter. Second question is determine the excess loss coefficient. In this case is the constant Kx. And finally, question C is the total excess eddy currents predicted loss when the material is assumed to be homogeneous. Well, here we have 3 questions, and you must be careful because the first question is related with Px, and remember in this case x is a lower letter, so in this case we are talking about loss density in watts per cubic meter. And then we have the question related with the excess loss coefficient. In this case is Kx. And finally we want the total excess eddy current predicted by Px. Px, as you can see over here, the letter X is a capital letter, so that means that we are interested on the total losses, and in this case the unit is watt. Okay, so in this line over here you can see the numerical results of the different answers for question A, B, and C. And in this case, we can start the solution of this problem step by step, okay? Okay, let's start the solution of this problem. The first thing that you need to understand is that the alternating iron loss density, Pi, in this case is defined in terms of power per cubic meter. What I am telling you is that Pi is basically the power densities, but in this case the unit is watt per cubic meter. You must remember that these loss density have three different components. One of them related with KH, this is basically related with the hysteresis losses. Also, we have here a term that is related with KE, that is related with some eddy currents, and KX, that is the excess loss. And you must remember that KH and KE, they were defined numerical values for them in question Q1. So again, it's very important that you must understand that using the provided values for KH, KE, and KX, this equation over here will give you watts per cubic meter. So we need to be careful because we know PI, and this is a capital I, and that means the total iron loss. That means the total loss in 1.85 kilograms. So if we want to use equation 1, we need to be careful because all the coefficients that we know, they are related with the case of watt per cubic meter. But we know the total iron loss, and also we know the weight. So we can be tempted to use the iron density that we know from the previous problem. If you remember, we know that there are 5 watts dissipated in 1.85. So in this case, if we want to obtain PI in terms of the units watt per cubic meter, what we need to use is what we already know from the previous question, from Q1. From Q1, we know that this material has a density equivalent to 7,800 kilograms per cubic meter. So using this equation over here, we can obtain PI in lower letter, and in this case the iron losses in watts per kilograms, dividing the 5 kilograms that we already know by the weight that we already know, 1.85 kilograms. However, doing so, what we will obtain is basically the loss density in watt per kilograms. And in reality, in order to use equation number 1, we must use the density of this material in order to obtain the active power loss density in watts per cubic meter. So in general sense, what we need to do is just appropriate numerical substitution in this equation. What I am telling you is that this equation, and let me call this equation number 2, the equation number 2 will give you the active power density in watts per cubic meter. And what we need to do is basically use the total iron losses that we already know is 5 watts, divide by the total weight of the sample, in this case 1.85 kilograms, and multiply by the density of the material, in this case 7,800 kilograms per cubic meter. If you pay attention to the units, you can see that kilograms here coming on the numerator of the density is cancelling with the kilograms here at the denominator of this equation. So finally, 5 times 7,800 divided by 1.85 will give you the active power loss density in watts per cubic meter. When you put those numbers in the calculator, you can see that the active power losses, iron loss, is equal to 21,081.08 watts per cubic meter. So now what we need to know, but you must be careful, this is PI. This is not the answer of the question A, because the question A is asking for the specific excess loss density, and in this case that is Px. So the next step, my dear students and all the viewers, is to use this very important equation that you already know, the equation that is combining the three different terms. And you must remember that this is the last term, and the last term is what we know as the excess adding current losses. And to be honest, we already know in the proper units PI, because we know that PI is 21,000 watts per cubic meters. So what we need to do is basically, we know the right side of this equation, and what we want to know is Px. So combining those two equations, well, is very simple to see. Remember, this term over here is Px, and we want Px. So we can obtain an equation, and this equation over here is very important, because this will be the equation that will allow you to calculate Px in terms of the total loss density, iron loss density, and here we have the hysteresis and the eddy terms. So now what we need to do is basically a numerical substitution, and this numerical substitution is extremely simple. I believe all my students can do that on the calculator. Remember, this is the equation that we derived in the previous page, and we know from Q1 the value of the KE, 1.65. We know the value of KH, 150, and also we know the value of the Steinmetz index, and this is coming from the question Q1. So also we know the operating point. We know that the maximum magnetic density is 1.2 Teslas, and also the operating signal is a AC signal with 50 Hertz frequency. So now what we need to do is just basic numerical substitution. We know 1.2 Teslas, we know the 50 Hertz. So when you put the number together, we obtain this magical number over here with the units that we were asked, and in this case is 4,727.8 watts per cubic meter, and that is the right answer for the question A. So it was a very simple process to obtain, in this case, what we call the specific excess loss, or also the known as the excess eddy current loss density in watt per cubic meter. So the next step is very simple, because we have been asked about the excess loss coefficient. And the excess loss coefficient, you can see over here, Kx, is a constant that depends on the material. And we can use this equation number 2. Remember the equation number 2. The equation number 2 is related to Kx, and that is the excess loss coefficient that we are looking for, the operating condition, in this case frequency and maximum magnetic density, and also the losses. So extracting the variable that we know and extracting the coefficient that we want to obtain, we can divide this term on the right hand side, on the left hand side, and Kx will be Px divided by Fm with this beautiful and exciting exponent 3/2. So now it's just a basic numerical substitution. We know this value because it's coming from the answer of question A, 4027.8 watt per cubic meters. We know F, 50 hertz. We know Bm, 1.2 teslas, and is just put together those numbers inside the calculator, and we obtain the answer for question B. In this case, Kx is equal 10.17. So we covered two questions here, and probably the final one is the most simple for my students, because we already know Px, that is basically energy loss density in watts per cubic meter. And now what we want to obtain is basically the total excess eddy current loss, Px. So it's just playing with the units. We want Px, capital X over here. What we need to do is use this Px in watt per cubic meter, divide by the density, and you must remember that the density is given in kilograms per cubic meter, and we multiply by the total weight of the sample, in this case kilograms. And as you can see over here, kilograms cancel with kilograms, and then cubic meters cancel with cubic meters, and the answer for this question will be Px in watt. So now what you need to do is the numerical substitution, very simple. We know Px, 4,727 watt per cubic meter. The weight is given 1.85, and we divide by 7,800 kilograms per cubic meter. So we put those numbers in the calculator, and this is a capital letter X here. We put the numbers in the calculator in order to obtain the total watts, and over here we obtain Px as 1.1213 watts, and this is the active power dissipated, the total power dissipated in 1.85 kilograms of the sample. So as you can see, those problems and those questions related with active power losses, they are very, very simple. And basically what you need to remember all the time is this equation that is extremely important, and also this equation that is extremely important. Those are the most important equations that you need to remember, but also the other part of these questions can be answered by common sense, that is basically using the units in order to obtain the requested values. So this is everything for this question today. I hope you enjoy. I hope that you learn something new and you enjoy this explanation, and I will see you at the next video. Thank you very much for watching, and bye now.